This is the Real-Time Calendar and Clock by Jonathan Colella.
We'll start with the inspiration. Timekeeping is one of the most widely used computer functions. Every single project, every program, every device relies on the ability to keep time in order to work. Computers without clocks would cease to function, so we often take for granted the ability to tell time precisely. Not only roughly, because humans can tell time just with the sun roughly. It's afternoon, it's in the morning. But what time is it exactly? Digital clocks grant us that ability. They let us tell time down to extremely granular levels like the nanosecond, even less than that, picoseconds even. That level of precision is not possible by any other means. No mechanical system can keep time that accurately. This project also definitely has implications for people in our scenario as well. College really revolves around you being punctual, revolves around you being on time. Making it to your classes, your exams, handing in your assignments on time is of paramount importance. And without digital clocks, it would be difficult for us to do that. So now we'll move on to a brief description of the project. So the function is that it displays the time. It's able to display the hours and the minutes currently. It utilizes the OLED display PMOD to actually print out the current time on the screen. And the way that it actually keeps time is using the RTCC real-time clock timekeeping PMOD. And all of this is married together, the two PMODs, and all of the glue logic are housed inside of the Xilinx Zinc 7000 FPGA. Now on to some problem solving. When I was developing the system, I ran into a couple of roadblocks. So learning how to use the Xilinx SDK was first and foremost the most challenging part of the project, since I had never worked with it before, and it's also been quite some time since I've developed in C++, so I had to sort of dust the rust off a little bit, but it turned out okay. I also had to figure out how to integrate the PMODs, since when you do a project with the PMODs and the AXI interface, you have to not only include them in your block diagram and have everything interface out in Vivado, but you actually have to account for them in the SDK as well. The program has to expect them to be plugged into a certain location, so that was definitely a challenge. And overall, understanding how to use the processing system of the Zinc device was a challenge as well. I'm very used to writing completely in programmable logic in Vivado, so it was definitely a big change to switch over to the other side of the hardware for this project. So now a little bit about the application space and what you might use this for. When you think about it, clocks are ubiquitous. Every human that's ever existed in the last 50 years, or even longer than that, has used a clock, right? Clocks are one of the most basic tools that we have, and they are one of the most useful tools, as simple as they are. Even going back to the picture here from, the humble sundial was an attempt to take something that we had, the sun, and use technology to get more precision out of it. If you think about it, all digital clocks really are an extension of the sundial. We've just come a very long way. When it comes to personal devices like watches, anyone can wear a watch, anyone can keep a small timekeeping device on them. And most modern electronics, by extension, tell the time. It's required for a lot of their functions. GPS wouldn't work without precision clocks. Mobile phones wouldn't work without precision clocks. Encryption, all of those fields require precision clocks. You can fit these devices in your house. You can fit them on and in your body. There are, nanobots and medical devices that you implant that have precision clocks in them. They really are everywhere. They're one of the most commonly produced devices ever. It's also interesting to think about miniaturization and ruggedization of clocks. You can find clocks in extreme environments both on Earth and in space. All satellites have precision clocks as well. So the market the end user, it's everyone. Everyone needs to keep time. Everyone needs to know what time it is. Having the precision time of day available to you helps everyone. When you do scheduling, when you have meetings in the corporate world, in the academic world, everything revolves around clocks. We all use time to agree on when to meet and when to do things by. We're also introduced to clocks from a very young age. Simple clocks can be used to teach time to children. Increasingly so, in recent years, we've been using analog clocks less and less, and it's been more and more important to teach children the workings of digital clocks instead. So, I mentioned it earlier as well, but even devices such as satellites can tell time, so the market really it's out of this world. It exceeds the bounds of the Earth. Here's a block diagram. So we have the OLED PMOD and the RTCC PMOD communicating with the Zybo, which houses the Zinc device. So they're plugged into the two PMOD connectors. I use JB and JD. Those are piped through the AXI interface, and they eventually make their way into the Zinc processing system, where I have a C program running on the ARM core, or one of the two ARM cores inside of the device. So the implementation, I implemented the block design in Vivado, then wrote C in the Xilinx SDK to be run on the core. So it's all off the shelf. The PMODs and the Zybo are both things that you can buy off of Digilent's website. They haven't been modified at all. So this specific implementation, including the code, is plug and play. I chose to use a general purpose processor, which takes the form of the ARM core, mostly because of the communication protocols involved. So doing SPI and GPIO, interfacing them, and then writing a program to do the bit manipulation for telling time and doing system calls would be pretty complicated and difficult to implement using only the programmable logic. So being able to go up to a higher level and abstract with the C code definitely makes things a lot easier. So I was able to benefit greatly from that. And this is considered a soft core instead of the programmable logic. So in summary, I found moderate success. I was able to complete the design and I loaded it onto the board. Debugging is a little bit challenging because with this, it tends to be kind of all or nothing. So I've been working on breaking it down to make sure that the PMODs are working correctly. Some things to look forward to in the second iteration of this would be increased timekeeping functions over longer periods of time. So looking at things like a calendar, what day of the week it is, what day, like numerical day it is. Taking into account things like daylight savings time. You can program in, if you know what day of the year it is, you can adjust the clock. In the same way, you can do time zone correction. You can tell the program what time zone you live in, and it'll bias the time off of UTC for you. There's also the 24-hour time format, which is popular, especially with the military. That would be something that could be added into this program as well as an extension. So some limitations that I ran into primarily was time, ironically. Lab 5 for this class was difficult to debug, so I spent a lot of time on that. There's also the space efficiency problem. So the Zinc board is vastly overpowered for a project like this, and it would definitely be possible to do it on a much smaller device. So that's something that in the future that would increase the usability by making it more compact, because it really is a very low power system. And the cost for the features attained, in the same vein, it's not necessary to spend over $200 on a Zybo if you just want to use it to tell time. There are FPGA platforms that are a lot smaller and cheaper that would also get the job done just as well. Thank you.